So this is just some more additional linear regression problems. The file can be found in the folder. Final exam practice materials. We're going to work through kind of all of these, and this will be kind of the last review I'll do for the exam, with the exception if anyone has any questions, if they're here live, you can ask those about any other practice exams. So we'll start here with these. If I see some questions come in, I'll kind of keep note of those, and I'll make sure we cover those specific problems. So, and I'll talk about a little bit about the exam at the very end as well. So here we've got some linear regression output from Excel. Hopefully, if you did that fifth Excel assignment, even if you didn't, or you did some of those practice problems on that practice connect assignment, they would all be examples where you get to run one of these regressions, and then you do a bunch of interpretation using those results. So I, on the exam, will have run the regressions for you, and we'll just be presenting you, excuse me, with the results. So here we've got the dependent variable is wage, which is measured in dollars per hour. The independent variables are education, job experience, age, and gender. Right? Gender is a 1 if the individual is male, and then 0 if they're female. Right? And all the other 3 variables are measured in age, in years. So if we look at here, just kind of going over a couple things. One measurement we want to know how to interpret is this R squared. So it's about 0.368 or 0.37-ish. So about 37% of the variation in wages are explained by education, job experience, age, and gender. So if we were to make a prediction about what someone's wage would be, we'd only be capturing about 37% of that variation in wage would be with just these 4 variables. Right? How can we make the most accurate prediction? Well, if we had an R squared of 1, or we could explain 100% of the variation, then we can make really accurate predictions. So we want to try to get this R squared to be as close to 1 as possible. If we look at the output here, I've got kind of my standard errors, my coefficients for each one of these different variables. So the very first question is, what's the correct interpretation for the coefficient on education? So the way that we do these interpretations is the same default every time. So the generalized form is a 1 unit increase in whatever X variable you're looking at would predict that the Y variable changes by whatever that coefficient amount is. So I kind of type right here, I'll kind of give you an idea. I did this for someone yesterday, I think it helped, right? So really what we're doing with this linear regression, we're estimating the following equation. So we're going to have the intercept plus the coefficient on education times education plus the coefficient on experience times experience plus the coefficient on age times age plus the coefficient on gender times that gender variable. Right? So if I can obtain these values for the intercept A and each coefficient, then if you give me a hypothetical person, I could predict what their wages should be, right? If they have 4 years of education, they have 14 years of education, 4 years of experience, maybe they're 30 and they're male, right? Then I could predict what their wage should be, right? And the interpretation of these coefficients, the reason why it's a 1 unit increase in the X variable, think about it this way, if education here goes up by 1 year, how much does wage change by? Well, if this goes from 4 to 5, then we're getting an additional beta 1 added into wage there. So every time this variable goes up by 1 unit, the wage or Y variable changes by whatever that coefficient amount is. Okay? So what would the interpretation be for education? Well, a 1 unit increase in education is 1 more year of education. We'll predict that the hourly wage goes up by $1.233. Okay? Hopefully that's somewhat clear there. Okay? So, and then that's the interpretation, and then we also have to add, because we have multiple regressions, holding everything else in the regression constant. So someone with the same years of experience, same age, same gender, but one of those people has 1 more year of experience, their hourly wage would be about $1.23 higher. Right? So holding everything else constant, every additional year of education is correlated with a 0.3. No, that wasn't it. Holding everything else constant, every additional year of education is correlated with a $1.23 increase in hourly wages. Okay? What would the test statistic be on the age variable? Well, we could look at actually any variable we wanted to here. The real kind of key, and if we look at the formula sheet, it reminds us to get the test statistic, all you do, right, is take that coefficient and divide it by the standard error. So, for age, negative 0.019 divided by 0.083 should be negative 0.229. And if you're kind of going through the rest of these, just to make sure you can calculate the rest of them, if you just divide the coefficient by the standard error, you should get this common test statistics, which I just had covered up here. Okay? Which of the following variables from the above regression, other than the intercept, would you reject the null hypothesis that there's no relationship between the variable and wages at the 99% level? So remember, we start off with this null hypothesis that every coefficient, and I said beta here, you can think of either beta or b, those are two notations that work there. We always start out assuming it's equal to 0. Okay? So if we go up here, we're assuming each one of these coefficients is 0. We found evidence that they're all, they're not 0. But was it strong enough evidence? So this is the same idea, whereas if the mean, say the population mean, we assume it is 50, well, it's very real that we could find a sample mean of 52, and that doesn't mean we should be rejecting that the true population mean is 50, right? It's pretty close to it. Same idea here, even though we're assuming it's 0, right? Negative 0.019 is pretty close to that. But is it close enough or is it far enough away? How do we determine that? Well, that's where we turn this into a test statistic, found the p-value, then we can compare the p-value to alpha and determine whether or not we reject it as being 0. So we look here at this p-value column. For education, 0.002 would be less than our alpha of, at the 99% confidence level, our alpha would be 0.01, right? 1% would be kind of outside the level in decimal form, 0.01. So 0.002 is less than 0.01, so we would reject the null, or we would find that education has a significant effect on wages. We would reject the null for experience because 0.005 is less than 0.01. We couldn't reject age, that's a really high p-value of 0.82, that's definitely not less than 0.01. And we would fail to reject for gender as well because that p-value of 0.179 is not less than our alpha of 0.01. Okay? So we can only reject for education and experience here. Right? So all we were doing there was really just taking the p-value, and if it was less than alpha for that variable, we rejected. If not, right, then we failed to reject. Right? Same rule that we've been using for all of our hypothesis testing, right here. Okay? So education experience. Right? Okay. So the next one, let's say we want to estimate the relationship between the SAT score and college GPAs. So we run the following regression, we find estimates for the coefficients are beta 0, or kind of A here, the intercept of a constant, is 1.5, beta 1 is 0.002, and the standard errors on the intercept are 0.65, and the standard error on that coefficient for SAT score is 0.00075. What will the test statistic be for the SAT slope coefficient? We've already talked about this one. If we want the test statistic, take the coefficient, divide it by the standard error. That's all you have to do. So here, coefficient of 0.002 divided by 0.00075 should be, these zeros are kind of messing me. I think it's 2.31, but yeah, not 2.31, sorry. 2.67 should be the answer there. So all we did there was take that coefficient of 0.002 divided by its standard error of 0.00075. Now I could have also come up with a test statistic for the intercept. There, what would I have done? I would have just taken 1.5 and divided by the standard error for that estimate, so divided by 0.65. So this is kind of a good one here. So using the intercept coefficient of 1.5, what would the interpretation of the intercept coefficient be? So the generalized form of the intercept coefficient is always if every variable on the right hand side, or all of our independent variables are 0, the expected value of the y variable would just be the intercept, or that beta 0 there. Think about it this way, back up in this example. If every variable was 0 up here, 0 times anything is 0, plus 0 times anything is 0, plus 0 times anything is 0, so on. So if everything else was 0, then the intercept would be, to the kind of expected value of the wage, or kind of where the wage would start before anything starts to take on positive values. Okay? Okay, so here the interpretation would be, if someone got a 0 on their SAT score, what would their predicted GPA be? It would be a 1.5, right? So the expected college GPA for a student earning a 0 on their SAT score would be 1.5. That's how we would interpret the intercept. So another question you could think about, for a student with a 1200 SAT, what would you expect their college GPA to be? So if we go up here and we start to make predictions, what we now have, right, once we have these values, is I've got the GPA is equal to 1.5, I just plug in that coefficient for the intercept, plus 0.002 times SAT score. Now I don't have the error term, right? We said when we're making predictions, our predictions will always be a little bit off from what the actual Y values are, because every individual has this kind of unexplained error, right? Error term. So if I have a 1200 SAT score, all I'd be doing there is plugging my 1200 into that, right? So I go ahead, take 1.5, add to that 0.002 times 1200, and I get a predicted GPA of 3.9 here, all right? So to make these predictions, you're really just plugging the values in, right? Plugging your coefficient values in where they belong, and then whatever hypothetical person here, it was a person with a 1200 SAT score, you would plug their score into the SAT variable. Actually, this is, yeah. Okay. Just get this one. No, we're gonna get that one. So assume the test statistic on the SAT coefficient is 5.75, corresponding to a p-value of pretty much 0. Right? An education researcher suggests that possibly if we just make the SATs easier, that would raise students' scores, and then that would lead to higher GPA. So what's wrong with this logic? So one thing we have to remember whenever we're looking at this, it's not that there's necessarily a causal relationship. It could very well be that doing better, getting another point on the SAT score, actually has not going to lead you to get higher GPAs. It's that you had some higher intellectual ability that would cause you both to do better on the SAT and do better in college on your college grades. So we have to remember that the regression only shows evidence of a correlation between SAT scores and GPA. It could be that intelligent students are getting high SAT scores and GPAs because they're intelligent, right? So it's not simply scoring higher points on the SAT score will get you a higher GPA. It's that those two things are going to be correlated. So it's just evidence of a correlation, not a causal relationship. We want to estimate the relationship between a child's birth weight and mother's age, where the birth weight is the dependent variable. So we've got 1,663 births. We run a simple linear regression. We find the intercept coefficient is 3,524. So I'd probably be a little bit less likely to kind of present the information to you this way. I would probably tell you this, but then I would also kind of give you, right? I could ask you, the only way I would give you something like this is if I asked you to select the correct estimation equation, and like knowing that the dependent variable, right, is your y variable, then you'll have your intercept plus the coefficient times whatever the independent variable is, which is here is mother's age, right? But usually if I'm asking you like questions like 8 and 9, I will have already presented to you what that regression equation is, right? And if I don't tell it to you, you should be able to figure out what it is by the dependent variable is your y, or left-hand side variable, and your independent variable is on your right. So if we have the coefficient of 3,524, what would that interpretation be? Well, if this was 3,524, it doesn't matter what the coefficient on mother's age is, we would interpret the intercept as if the mother was 0, the expected birth weight would be 3,524. Now, obviously, this is a crazy interpretation, but I've walked through a couple, showing you the scatter plots of what the data would look like when you're estimating a line of best fit, and the reason why that interpretation is weird, and so it doesn't matter, that's still how we interpret it, okay? If all the other variables were equal to 0, the intercept is the expected value of our y variable. So, we'd have b there. Alright, A researcher finds that the test statistic for the slope coefficient on mother's age is 2.54. The researcher concludes that as the mother gets older, her children will have a higher birth rate. What's wrong with this logic? Okay. Well, once again, this is just another example of, right, it could be that just because we find a positive slope coefficient on mother's age, we talked about this with the athletes, student athletes at college, right? It could be that an older mother is correlated with a lot of other things, having a higher education level, having a higher income level at that time, which are all going to be better for kind of prenatal care. And so it could just be that mother's age is correlated with a bunch of other things that are impacting birth weights. So once again, the regression kind of only provides evidence of a correlation between a mother's age and child's birth weight. It could be that as she gets older, she gets a higher amount of education, more responsible, etc., etc. Right? So if you see a question like this, hopefully these shouldn't be too tough. You're really just trying to tell me or find the option that says this is not a causal relationship, it's just evidence of a correlation. So that would be D there. So we've got another example here of the dependent variable being crime rates, and then our two independent variables being police force expenditures measured in dollars per person, and the unemployment rate, which is measured in kind of percents, right? So it's not going from 0 to 1, it's going from 0 to 100. So what would the interpretation for the police expenditures coefficient be? Well, if I look here, 12.63, right? The way I interpret these coefficients, remember, is a 1 unit increase in my x variable. So if the x variable goes up by 1 here, it would be, well, what's the unit? Dollars per person. So if the county spends $1 more per person, they can expect crime rates would be about 12.6 per 100,000 people higher. So I probably won't give you kind of these rates, but this is a good example of one where you can just get a slightly different style of interpretation because the units that these variables are in. Notice again, it's just kind of a coincidence, but the R squared here is similar to what it was in the other regression, right? We were explaining about 37% of the variation in crime rates just with police force expenditures and the unemployment rate. Okay? And I left these open-ended. You can kind of imagine I could kind of come up with some multiple choice, but I just wanted to give us more examples that we can kind of work through, right? Right. If you can solve a short answer problem, hopefully it'd be fairly easy to solve a multiple choice question. Right? And I may have a couple short answers like this at the very end of the exam. I mentioned in an earlier video. You might have to upload, kind of similar to exam 2, some short answer responses. So what's the interpretation of the intercept? Well, remember, the interpretation of the intercept is if every other variable is equal to 0, so if we spend $0 per person on our police force, if the unemployment rate was 0, the expected crimes per 100,000 people would be 3,230, right? So if all the other variables are equal to 0, right, then these two values would be, if all the other variables are equal to 0, then this value, 3,230, would be the expected value for our dependent variable, which was property crime rates. Once again, if we wanted to kind of write out the equation that we were estimating, I don't want to do that. Property crime is equal to the intercept plus beta 1 times expenditures plus beta 2 times unemployment rate, right? What would the test statistic be on the unemployment rate variable? Once again, this one should be easy. Coefficient divided by your standard error. 6.9 divided by 116. All right, so it's going to be really small. If I move the box that I put over here, right, 0.059. Very low test statistic, which means we have a very high p-value. Right? So if we looked at these p-values, we would say that the unemployment rate, right, really isn't a good predictor of crime rates, holding constant how much the town is spending on their police force. However, when we see these e to the negatives, remember that means move that decimal point 6 places to the left. So this is pretty much a p-value of 0. So we only reject the null, which remember the null is that the coefficients are equal to 0. So we can't reject the null for the unemployment rate. We can't say that it has a significant effect on crime rates. But police force expenditures we can say has a significant effect on crime rates because that p-value is pretty much 0, which will be less than any alpha we could think of. Now, I say it has a significant effect, right? It has a significant correlation is probably the more accurate way to say that, right? Because this is just evidence of a correlation, right? It doesn't make sense that if I spend more on my police force that crimes are going up, but it's probably because we're not including a lot of other things here that are correlated with police force expenditures and correlated with crime rates that matter. So that's kind of why we're getting that. So that's 13. So let's say we have the next regression, right? So we have the next regression here, which is football revenue is what we're trying to predict, and we're trying to predict it using male enrollment. So what would you expect the sign and size of this coefficient to be? Well, let's think of the interpretation. Right? The interpretation of beta 1 is one more male student, right? This is 1 units measured in student, number of students, so one more unit is one more student. We'll predict that football revenue will go up or down by whatever beta 1 is. Now, I would think that even if this wasn't just male enrollment, but if it was just enrollment, the effect of having more students at your university, they're likely going to be spending money at the game, or potentially that's evidence that you're at a more popular school where you might have more people coming to the games, and so higher enrollment is likely going to predict that revenue goes up. Now, what's the effect of one additional student? My guess is it'd probably be relatively small if we had a bunch of other control variables in here, and I would actually say you expect the sign to be small. And if you gave the reason as to why, it's because it's only one student, right? But if we think about, well, even if it's just one more student, if we have subsidies and things like that, it actually could be that from the student fees, you're actually adding quite a bit, and we actually look at this estimate, that is actually pretty high, right? Now, I'm not going to ask you an open-ended question like this. I'm just kind of getting us to think about things, about what the size of these are before we even look at it. But what I could ask you is to interpret that male coefficient, or male enrollment coefficient. So we already kind of did this. If I have a 1 unit increase in male enrollment, so one more student would increase my predicted football revenue by $2,621. And what's the test statistic? Well, once again, I have it here, I didn't hide it, but you would just simply take your coefficient and divide it by your standard error. Right? So these are just example questions. So here, 2,000, right? We would do as I'm talking, you can kind of see. So 2,621. 0.77 divided by 34.06, right? And we get that huge test statistic, right? So suppose we, actually, I'll get rid of this one. I didn't mean to include that question in here. That was stuff that we haven't covered or we're not going to cover, okay? So I'll re-upload this if you're following along right now. I'm going to delete 16. You don't have to worry about that one, okay? And we're explaining a lot of the variation, right? So just with male enrollment, we can explain almost 50% of the variation in football revenue at the school. So now suppose we include not just male, but also female enrollment, right? So we're capturing the entire enrollment at a university. And then we're also including men's basketball revenue. So there's some interesting things we could think about here, and it's the reason why I did that. It might not be completely clear yet, but it kind of relates to some economic principles, which I'll mention. So we've got male and female enrollment here. So if beta 1 is greater than beta 2, what that's saying is that an additional male student would increase football revenues more than an additional female student. Okay. So we go down here, look at this, sure enough, we actually have a negative sign on female enrollment, which seems kind of odd. Male enrollment is still pretty strong and positive. Now, the interesting thing is if we look at the actual p-values here though, can we actually say that female enrollment has any impact? Holding constant male enrollment and holding constant, men's basketball revenue, the p-value is 0.23, so we can't say that this is actually significantly different from 0 at any confidence level that we would want to, right? Not at the 90, not at the 95, not at the 99. Okay, so we find that that has no impact on football revenue. A change in female enrollment, at least at significant levels. Men's enrollment, see that estimate has fallen a bit. still fairly high and also still very significant, right? The p-value is still 0. So we would still say that we could reject the null, that the relationship between mail enrollment and football revenue is 0. We can reject that. We find strong evidence that there's a positive relationship. Notice just including these 2 additional variables, our R squared is now at 63, about 0.63, so 63% of the variation in football revenue we can explain with these 3 variables. And then men's basketball revenue also looks like it has a positive effect on men's football revenue, and the p-values are pretty much 0. So what would the test statistic on male enrollment be now? Well, once again, same thing we did before. It doesn't change anything that we did. Still take that coefficient on male's enrollment divided by the standard error. Once again, you'll get your test statistics that I have covered up over here. Okay. So these test statistic ones, hopefully, you're seeing it's pretty easy. And I'll get a kind of answer to this hopefully later today, at the very latest tomorrow. But if not, you can kind of listen to this, walk through it. I think just listening to what I'm saying, it should be pretty clear how we calculate that test statistic. So how much more variation does including female enrollment and men's basketball revenue explain about the variation in football revenue? Well, if we looked at the R squared here, it's 63%. The R squared here was 0.49 or 49%. So how much more does it explain? Well, if the new model with the additional control variables explains 63%, and the old model only explained 49, I would just take the difference between those two, which 63 minus 49 is 14. Right? So how much more variation? 14% more. Right? Now, I wanted to point out one thing here too. It's kind of interesting. This relates to stuff that maybe you've seen in other classes. If we think about complementary goods or things that are complements, notice here men's basketball revenue is positive. So this is kind of implying that if we have larger men's basketball programs, that also has a positive effect on how much revenue our football team is generating. So maybe there's some complementarities in having good sports programs, but also that's holding constant what the enrollment at the school is, holding constant male and female enrollment as well. So I thought that's kind of an interesting example. I had some of the data laying around. I think, this exam, so a little bit more so than the practice exams, you notice those practice exams ended at like questions 25 or 26. The questions that would fill it up to get to about a 30 question exam are going to be linear regression stuff. So the majority of this exam is going to be linear regression and 2 population hypothesis testing. And then, about 12, 13 questions are going to be old material that look very similar to the problems that are on both those practice exams in terms of kind of the content that's going to be covered. Obviously, slightly different numbers, slightly different examples, but the content will be the same. So study those practice exams when you're wanting to study the early material. And then for the linear regression and hypothesis testing, right, we've got some stuff on the practice exams, but you also have these additional problems here. I would even go back through, I'm going to get this final example on Monday, but because I have the Excels due Sunday, I'm going to have the answer keys set to release probably a little bit after 12, just in case someone has like a technical difficulty, I don't know, uploading. This doesn't happen, but I wouldn't want the answer key to be out there and then kind of panic because they're not able to get their thing downloaded. I've had a couple times in the past had really late emails. I can't get something to upload, because of their computers having issues, and then usually they resolve it within the next 30 minutes or something. And so I'll have those released that night, and that way Monday you'll have those to look over as well, right? The answer keys, because even though you did the work in Excel, the principles, the equations you were using, especially on that 5th Excel assignment, the linear regression, that's just more practice problems really of doing in Excel what you would be doing by hand on the exam, right? In terms of the interpretation of the results, right? So not running the actual regressions part of the 5th Excel assignment, but the additional questions that follow would be good study material. Okay, so I'll get this weekend posted up, the exact release time on Monday of the exam, but I will get it posted sometime on Monday. Once you start it, you will have an hour and 30 minutes to finish it. Actually, sorry, I'll do 2 hours. I'll make it 2 hours because usually we have a 2-hour exam time slot. So I will do once you start it, you'll have 2 hours to finish it, right? Timing shouldn't be near as much of an issue. I mean, if you think about past exams, it was 20 or 20, 25 questions So we were doing that in an hour and 15 minutes here. 2 hours to do 30 questions. I think it should be okay with time for most people. Once you start at 2 hours, you can start at any time though. So once it's posted Monday, you can do it Tuesday, you can do it Wednesday, you can do it Thursday, you can do it Friday. You can do it any time next week. Okay. And so if you have any questions during the week as you're studying, please feel free to email me. We can set up some WebEx meetings. I've done that with quite a few people this week, working on some of the Excel assignments. So you can take that exam. I don't know how other professors, if they're doing a more stringent kind of time window. I don't think they're really supposed to, but we can, you can kind of pick and choose when you want to organize your schedule next week, especially this exam, because you can take it any one of those days, right? But once you start, 2 hours, and then it's up. Okay. I won't be kind of locking it down as before because I want you to have the materials. Like I said, I'm not going to use the respondus on it, so you'll have all your materials available to you. Student T, standard normal tables, all 3 formula sheets, and they're all in that folder too. So you make sure before I start the exam, download all of them. Don't open them up in web browsers. I would download all of them and have the files actually open. Maybe you have them open in web browsers too, but just in case, I would have them downloaded and ready to go as well. Other than that, feel free to reach out to me as you're studying, and that should end it for this exam review session number 2.